The name, I think, is pretty clever, but at some level, we're all trying to figure out what it is. But I think links together climate systems, obviously kind of really well understood piece of science, and systems engineering, which is somehow the idea of thinking systematically about the link between goals and outcomes.
Welcome to the Challenging Climate Podcast, where we discuss the big ideas and controversies in climate change with leading experts. I'm Jesse Reynolds, an environmental policy specialist.
And I'm Pete Irvin, a climate scientist. The climate is changing. Join us as we try to keep up. In this episode, our guest is David Keith, a professor in the Department of the Geophysical Sciences at Chicago and the founding faculty director of its new Climate Systems Engineering initiative. David has worked at the interface of climate science, technology, and public policy for over 3 decades and is at the forefront of efforts to advance the science and policy analysis of solar geoengineering. His work has ranged from the climate impacts of large-scale wind power to the elicitation of expert judgments about climate change and much more. He is also the founder of Carbon Engineering, a company developing technology to capture CO2 from the air.
David is also a co-host of the podcast Energy versus Climate, which you may have listened to as we featured it as a crossover episode recently. And finally, as a disclaimer, both Pete and I have worked with David in diverse professional settings. And now, our conversation with David Keith.
Well, David, welcome to Challenging Climate.
Happy to be here. Glad you folks are doing this.
Well, great. We just want to launch straight in. You've got a new position at University of Chicago at the Climate Systems Engineering Initiative. What is Climate Systems Engineering?
I'm still trying to figure that out. They hired me to run this thing. So what it is a really quite major new initiative that UChicago has done that will cover both solar geoengineering and some pieces of open system carbon removal and some of this ice sheet intervention, aka geoengineering. The name, I think, is pretty clever, but at some level, we're all trying to figure out what it is, and it'll be kind of iteratively figured out by who comes. But I think links together climate systems, obviously kind of really well understood piece of science, and systems engineering, which is not perfectly defined, but is somehow the idea of thinking systematically about the link between goals and outcomes, thinking systematically about uncertainty, kind of applied engineering style technology and policy analysis. There are departments of systems engineering around. So I think at some level, it's about kind of linking those two things together. But broadly, you could think about it as the geoengineering department. But I'd say one funny thing for me is I've spent, as you both know, years trying to really push CDR and SRM apart. And now I'm running a thing that has them both together. And so far, that seems pretty good. I guess I enjoy eating some crow.
So it's more than just the sum of the parts. It's not just a CDR plus SRM department. What other techniques are you considering? Does it go beyond CDR and SRM?
I'd say the really big thing is it's the first time that a really big research university has decided to commit to this field, whatever exactly it is, in a serious way. So the idea is to hire, in the end, something like 10 faculty. We have an active faculty search going on that's kind of university-wide, so any discipline in principle can apply, and we've got applications from across disciplines. And, in a large measure, academia, things are really determined by who comes. So I'm hire one, but my fundamental goal is to hire new people and kind of get out of the way and to help make this field in the way it hasn't been before. So some of the exact questions about what's in and what's out, what we end up studying, won't be based on whatever I tell you now, although I can give you my 2-bit opinions now, but they'll be based on who actually shows up and how it evolves over the years. I think the fundamental thing is a university making a commitment as part of a larger climate and energy institute to really build an effort that has this kind of center of gravity where there could be, order 10 faculty. So to think of that with postdocs and students and some practitioners, kind of 100 class people, that really, I think, will change the way these things are talked about in ways that might be unexpected and, give a kind of larger room for diversity of opinions and so on. So that's a kind of long-winded answer. Maybe to cut to the short answer about what's in and what's out, we've been saying that we're talking about is open systems carbon removal, meaning particularly, say, enhanced rock weathering or ocean alkalinity. And the underlying thinking there to have those in and say DAC out is the following, that these open system carbon removals involve some of the same deep questions about environmental science and geoscience and this complicated questions about intervention and side effects. And in some ways, they're quite a lot like solar geoengineering. They're not like solar geoengineering. They don't have this kind of high leverage. So enhanced rock weathering costs enough money. There's sort of no worry that people will go do so much enhanced rock weathering and they'll suck all the CO2 out of the atmosphere for free. So it doesn't have that high leverage challenge that solar geoengineering does. But in terms of assessing how well it works and so on, it's got some of the same richness. In a sense, it needs a really broad breadth of disciplines in a way that I think direct air capture does not. Direct air capture is primarily an engineering challenge. There's complicated policy about whether you should use it and what it will cost and so on. But in terms of the science of it, it's mostly engineering. It doesn't require kind of integrated or systems knowledge. That's the logic to have these open systems in and not direct air capture so much.
Yeah, so by open systems, it's these efforts where your mode of action is by changing the Earth system in some respect. That's how you achieve this result, rather than it being an engineering facility like direct air capture.
Exactly. So I'd say a thing that cuts across all these different things is about humans deliberately intervening in the Earth system in some way. And you can think broadly about these deliberate interventions could either be restorative or transformative. So, in principle, humans have, of course, intervened in nature with the goal of transforming nature, since we did for agriculture and many other things. I think the goal of the things we're talking about are all restorative. That's not to say they necessarily will restore or they will work, but the goal of solar geoengineering or of these climate system engineering efforts that we're talking about for, say, enhanced rock weathering are to try and somehow push the Earth back towards the pre-industrial.
I guess a thought here, for most of the work I'll focus on solar geoengineering, has been done by climate scientists, trained as scientists. Is there a bit of a cultural or paradigm shift in switching to this kind of interventionist set of approaches? I mean, I guess I'm thinking the systems engineering side kind of hints at that. Will there need to be a cultural shift in the research community to really address these well? Or
I do think there's a way in which just is fundamentally different from science, in the sense that with classic pure science, you're trying to understand how nature works. And with classic climate science, you're trying to understand how nature works with the particular incentive that you want to understand how nature will respond to all these gigatons of climate pollution that we're pumping into the air. But in some sense, you're still really just talking about how the natural world responds to some insult. But I think as kind of climate systems engineering or environmental engineering framework, you're trying to think about how humans can interact with the natural system in a way that reduces impacts or offsets impacts in a way that's different from simply minimizing the human activity. And so I do think that it does require a different kind of thinking that is somewhere in between kind of classic science and kind of narrow engineering. Because as you know, for solar geoengineering, you can't study how solar geoengineering would work without a whole bunch of fundamentally engineering assumptions about what is difficult and hard and what choices people might use to do it. And solar geoengineering is not a thing out there in nature like peregrine falcon where you can study how its eyes see prey.
Well, there's some other differences in the sense that, I mean, I think maybe you know more about this than I do, but engineers have certain responsibilities for their creations. Are there some sort of moral and ethical implications of that switch to an interventionist look at the Earth system?
Yeah, I think there should be. Of course, as you know well, there's a big line of people who think that one of the problems with calling it geoengineering is that somehow engineering connotes that we know everything and that it can be engineered perfectly. And so that is somehow an overselling, and that's why we shouldn't use the word engineering. I don't actually buy that at all, because I think in practice, engineering actually taught in engineering schools deals with all sorts of things with quite high uncertainty. And modern engineering schools, certainly not perfectly, but modern engineering schools actually have required courses on social consequences of what you do and on how you think about design with the clients, if you like, or with society. I don't want to defend it all as all fine. There's obviously lots of terrible stuff that comes from engineers, but in a way that really is different. In science, if you're taking a hard science classes, you're not required to learn any of that. But in a standard engineering degree, and at least the places I'm familiar with, you actually do need to learn. And so if you're somebody who's working on either engineering a dam or engineering a driverless car, I don't want to make it sound like engineers all do the right thing. They obviously do not. But there's at least a structure in engineering that says that it absolutely is the job of engineers to take some responsibility for the consequences of the engineering system and even to think about the kinds of ways it might be misused, not just its intended use.
So let's work through some of these top-level categories of climate system engineering that you've mentioned. I started with some attention to what you call open system CDR, which brings to mind the categorization. Of course, there's always been lots of categorizations of some of these techniques of Steve Rayner, who divided these proposals between He talked about black box engineering and enhancing natural processes. So, am I right to think that what you mean by open system CDR are those efforts that would enhance or leverage natural processes, or is it a bit broader than that? Help me out here.
I'm trying to think of counterexamples, but I think the simple answer to your question is yes.
Okay, good. CDR, carbon dioxide removal, has, from my perspective, just really skyrocketed in the attention that it's receiving within the climate change community. Within this conversation, however you want to measure the metric, popular press or scientific articles or pages in the IPCC or whatnot, what aspects or methods within CDR do you see as not receiving enough attention? What is undervalued in carbon dioxide removal?
Well, I can say something based on what we're doing right now. So one of the things in starting this program, I'm trying to hire people and all sorts of stuff, but we've been running kind of focused topical meetings, bring together a relatively small number of diverse experts. So we ran one on ice sheet engineering that was just really thrilling about 3 weeks ago. And we have one on enhanced rock weathering and ocean alkalinity that's coming up in about a month. And it's been just thrilling. Everybody seems to want to come. We're going to turn a lot of people away. But I'd say two things about that may be useful. One insight that the 3 or 4 of us organized in the meeting have is that there's an important way in which enhanced rock weathering and ocean alkalinity should be compared because they have the same endpoint. So let me just some background here. So the endpoint is to add alkalinity to the ocean. Indeed, the very first little memo I had, this was called drowning cats in the ocean or something. It was a joke because of cat ions. But the point is that in the long run, one of the ways CO2 is permanently removed in the Earth system is because CO2, a weak acid, can be balanced by bases dissolved in the ocean. And once that's done, you more or less are at a zero risk permanent removal of CO2. So there is all these rocks that have bases, and they thermodynamically want to weather in the presence of atmospheric CO2 of the acid. And so the most obvious thing you do is grind up these rocks and put them in the ocean. And the problem with that is while it is thermodynamically favored, in a sense it wants to happen, it's negative energy, the kinetics are very slow. So if you grind up some of the rocks to even 100 nanometers, which is a tenth of a micron, where grinding costs really start to just get extremely large. Even at that scale, if you drop these little submicron particles in the ocean, they'll sink to the bottom before they react. The reaction is just too slow. So one way to think about the whole point of enhanced rock weathering is it's one of the ways around that. So you grind the particles up to just millimeter size, which is the typical size. You put them in agricultural soils where they're kind of, if you like, suspended in wet surface with some CO2 contact, and they could react. And then the reactant, the bases, will run off the land into the ocean where it will neutralize. So the end point of either enhanced rock weathering or electron alkalinity is to add these cations to the ocean. And I think saying that helps to frame the idea that we should compare the environmental impacts, the difficulty of quantifying these things, and the cost of them. We should think about those in a comparative way because the endpoints are the same. So that's a very general theoretical thing. I can say a really exciting thing for me in the last few months leading up to this workshop has been understanding just how extraordinarily fast things are moving in enhanced rock weathering. So partly it's been kind of thrilling. I worked on some of this stuff, reviewed some papers and did some work 15 years ago, but I haven't been paying any attention. But in a way, frankly, because of the carbon engineering thing, people know my name and everybody seems happy to speak. And so I've been going around just talking to people, and I went to a little meeting EDF had and talking to a range of people, proponents and opponents and whatever on enhanced rock weathering. And I had no idea, and my guess is some of your listeners had no idea, how much is happening on the ground. So it'll be more than 1 million tons of actual commercial removals this year, might easily double next year. It's happening at an extraordinary pace. There's a whole mass of startups, and there's a literal movement of multiple academics leaving academia to just jump in and do this. So much so I think one of the challenges that we're going to try and work on in the workshop is to articulate clear roles for the need for academic science to understand environmental impacts and risks, separated from the legitimate use of these companies. But people can't do both. Once they're in a company, they're advocates. But the pace of change has really been amazing. I can't remember who it was said to me, this is really easy to start a company. You basically need to make a deal with a granite mine that's got some waste granite they want to get rid of anyway as little chips. You buy yourself a ball mill, you make a deal with some farmers. They've got the agricultural equipment already, and then you connect the voluntary carbon market, and presto, you've got a business. And that's all great, but there's so many questions about side effects like toxic metals, about the rate of reaction, about the extent to which these things are independent. If I'm doing it as a farmer and you're the neighboring farmer, how much does that increased alkalinity alter the chemistry of the water downstream? There's questions about reverse weathering. There's just a host of scientific questions that are being inadequately examined.
In the carbon dioxide removal conversations, I see two, maybe three concerns that repeatedly crop up, and I'm curious, get your take on these. One of which is the realistic scale of CDR of various types over the next few decades. Do you think that some of the scenarios used in climate policy lean too heavily on assumptions of CDR scale up?
Of course, I don't think those scenarios are taken very seriously by people except who want to sell CDR. So at some level, there's a construction that happened where there was a political decision to aim at 1.5 or 1 or 2, depending on how you like it. Perhaps a very wise political decision. I don't want to question that. I think there's an inherent deep logic about, as I was putting the feed bag of the donkey. I don't know if anybody's seen these feed bags tied around donkeys' noses, just a little bit ahead of the donkey, so it kind of keeps moving. So we're people who made that 1.5 deal, I think, not expecting the world would actually do that, but by having a near-term target, it helps to build near-term energy to cut emissions, which I think has actually been successful. There's all this stuff happening on emissions cuts. But then people, of course, through IPCC 1.5, which wasn't, as you know, scientists saying we should aim for 1.5, but scientists answering the question, what would it take? If you want to meet 1.5 and you are not allowed to use solar geoengineering, especially if you then change the goalpost by saying you want 1.5 at the end of the century, so you're allowed to overshoot, then you kind of automatically get to a world where you solve the equations, you get a massive amount of CDR. That's the correct solution to those equations, but I personally don't think it's a sensible prescription for policy. So in the CDR community, there's tons of, especially business presentations that just start by saying, scientists say we must have 10 billion tons of CDR by 2050 or whatever number they choose. Obviously, scientists don't say that. These are political choices. And I personally think that the idea that we're going to have 10 billion tons by, say, 2050 or 2040 is very unlikely to be good policy.
Another issue, particularly with open system carbon dioxide removal, is verification. It can be difficult to measure how much carbon has actually been removed by intervening in a natural system. Do you see this as a substantial barrier to the scale up and potential commercialization of techniques such as enhanced rock weathering?
It depends. It's certainly the right question, but I don't think the answers are easy and they differ for the different techniques. So there's a way in which, at least for some versions of direct ocean alkalinity, if you put a mole of alkalinity in the ocean, you can be really sure that in the long run, you're going to remove that kind of 1.8 moles or so of CO2 because of the carbonate by carbonate ratio. There's questions about the time scale of doing that. But one way to think about it is people have different timescales they care about. There's not a naturally right timescale. So it feels like that uncertainty is very different from some others because you really are sure that you are doing permanent carbon removal and you're even sure the long-term quantities. For enhanced rock weathering, there's even bigger uncertainty added to that because of the uncertainty of the weathering rates, but those are also in principle measurable. So the answer to your question is, yeah, that's an issue, but A, it's going to vary for the different methods. Some methods it won't be such an issue for. And B, you're implicitly assuming, by sort of saying that's a problem, that this will work in a pay-for-ton basis. But at least my view is that if large-scale ocean alkalinity ever happens, it should work on a pay-for-performance basis. There's enough questions about what the environmental impacts are. I don't really want kind of free capitalism just trying to do all the accounting, because the accounting needs to be done by cleaner, transparent science. So I think that it makes sense for, in the end, governments or through markets to pay for performance. That is, put X million tons of this particular calcium oxide compound in this part of ocean with this specification. And our scientists will separately say what that is in terms of long-term carbon removal with uncertainties, but we're not going to pay you by the ton, which forces the company to claim that it knows how to do all that science, which I am never going to believe. The difference between pay for performance and pay for tons is who's taking responsibility for that uncertainty.
Maybe just elaborate on the timescale here, because if it's definitely capturing CO2 in the long run, there's different timescales of long run, right? I mean, within the next decade is one thing, within the next millennia is quite another. Is there a risk that, I think we're seeing this now in the, voluntary carbon offset market, especially around, tree plantations and so on. Is there the risk of a scandal around this stuff? If people make grand promises, this kind of relatively unregulated space rushes ahead?
Yeah, I think there's a bit of a bubble. It's also important to be clear about how small it is. So last year, Bloomberg Energy Finance number, the total global spending on clean energy was about 1.1 trillion, which is an absolutely stunning success. The single most important thing in my entire lifetime of climate policy, a third of a century I've been doing it. You just can't overstate what a big deal that is. More than 1% of GDP. And that's basically batteries, solar, and wind, more or less equally split. And it's just fantastic. And it really changes my view of the whole climate problem because it means we're actually doing something. I don't know the total flow of money into long-term carbon removal, but I and others who sort of guess it would say it's certainly less than 10 billion, might be just a few billion. And so I think objectively, this is all pretty small still. Personally, I think it should stay small for a while. That is, if you asked me as a voter to say what the split should be between effort to cut emissions and effort to do CDR, say 10 years from now, I would personally put, I don't know, 95% of my effort into cutting emissions and 5% into CDR, just winging it today. I might give you a different answer tomorrow. With the idea that there's, in the long run, we want to develop CDR technologies because we really, I think, will as a species want to undo the damage of putting a CO2 in the atmosphere. But in the short term, in terms of actual action, it makes more sense to stop emissions than to do CDR. So I don't know if you agree with my 95, feel free to two-way podcast. You can put your own number on. But the point is, if you agree with any number like that, the number that's actually being spent is still much less than that. So there's this weird dichotomy of people complain that it's overhyped. And I think it is in a way in terms of the talk. But in terms of spending, I think it'd be pretty hard to argue that 0.05 or 0.03%, which is the current number, is actually too big.
Yeah, I guess I'm speaking about the incentives and the finances of this. After we hit net zero and global temperatures peak, do you think countries will have a strong incentive to drive CO2 concentrations down? It's going to be quite a lot more expensive than preventing them from increasing, right?
When do you think we'll get to net zero?
2075. How about that?
I'm not going to be here. You might still be here with some luck. So will it be more or less expensive, assume not in current dollars, but I think a fraction of GDP would be the right measure, to remove a ton of carbon then as now? I don't think that's clear. It actually may be cheaper to do it then. Technology does move along. Economy gets bigger. Economy gets bigger relative to the energy sector. That's the whole long shift to services and so on. So I think it is probable, indeed, my guess is it is highly likely that if you want to ask what fraction of GDP does it take me to remove a gigaton a year in 2075 compared to the cost of avoiding a gigaton a year of emissions in the next little while, my guess is a fraction of GDP, it's a lot cheaper in 2075. And these technologies really do move. I think you can easily imagine that there's ways to do, say, large-scale ocean alkalinity that are well under $100 a ton carbon.
All right. Well, changing gears, solar radiation management. Now, I guess I'm wanting you first to reflect on it. Does the overarching term solar radiation management, is it useful, or do we need to think about two distinct categories, a kind of a global category and a regional category?
Well, yes, there are those two categories. And yes, I think an overall term is useful. I think there's a lot of similarities between all the different ways that humans might deliberately alter radiative fluxes. And again, what do you call it? Solar radiation modification, which is the IPCC version now. Yeah, I think there's clearly a lot of relevant subcategories, but I think there's a lot that connects all the different ways that humans might do large-scale modification of radiative fluxes, whether you want to call it solar radiation modification or planet hacking or SRM or whatever. I don't really care. I don't think it makes much difference. But I think there is a lot that connects them. So I think the big category is useful, although there are, of course, subcategories underneath it.
So yeah, you've been studying, I think you focused mostly on stratospheric aerosol geoengineering in your research, which you've been studying since the 1990s. Was that your first paper?
Well, I started working on stuff in the late 80s, actually. The first good draft of the first paper was, I think, about 89.
So you've been studying this for probably longer than almost anyone else. Did anyone else? Well, anyway, certainly a long time. I guess the question is, how has our understanding changed? What are we now confident of regarding its effects? You know, hundreds of papers are now out. What are we pretty sure about stratospheric aerosol geoengineering?
More like 1,000 papers out. Yeah, that's a good question. I mean, to be clear, I didn't focus on it the whole time. I did put a lot of effort in that early paper. We're in kind of 1989 or something. But then there were a lot of years where this was sort of 5% of my time. And then the last 15 years, it's grown to be most of my time. Well, other than carbon engineering. But I think we know much more about which methods are doable and not, starting at kind of technical feasibility, I think there's actually been much less than there should be. I mean, one of my big complaints is that we just sweep the engineering under the rug, and there's like just easy work that could be done on engineering, but that doesn't fit into science, so it doesn't get done. And so there's just a whole lot to say there. But still, I think we do have a bigger sense of what might be sort of feasible and not an engineering sense. That's maybe not the most important thing, but it's a fact. And I think we have a much better sense of how well these things might actually work. And I think in some deep level, there's a really big surprise, at least for me, that they seem to work much better than I thought, or I think many other people thought, or even than I wrote. Obviously, we don't know how they work, but we never will know exactly how they work. It's always going to be based on models and inferences. Even if we do it, it's going to be based on models and inferences. But the point is that all sorts of things that were concerns about, especially the extent to which the effects were necessarily highly unequal between regions and some of the scale of some of the side effects, I think in many cases, when we've looked at those carefully, they look quantitatively smaller than we thought. I think what's really interesting is if you compare what was known, say, around 1990, I wrote that review article when there was these, early Academy reports after the 1982 Academy report, to what we know now. If you wrote down the list of concerns, I think the list of concerns would not look that different. There's certainly some more detailed sub-concerns, but the kind of high-level concerns about inequality of effects, about acid rain, about air pollution, about changing the color of the sky, et cetera, people thought about all those problems right at the beginning, if you like. And what I think is different is there's now been at least some real research using existing, well-understood chunks of science on almost all of those side effects. And in general, they come out looking smaller than many of us would have guessed.
On stratospheric aerosol geoengineering, where might we expect big surprises? What are the big uncertainties that are remaining?
The problem with surprises is it's really hard to expect them. I think a really important thing the community needs to do is stop kind of rerunning models on just slightly politically different scenarios that all more or less say that relatively uniform solar geoengineering works pretty well in some crude sense to reduce climate risks, and focus on the question of what the probability of really surprisingly bad outcomes is, because I think that's the central thing that public and policymakers will want to know. I think for the kind of the behavior of aerosols in the stratosphere, if you're talking sulfuric acid aerosols, it's a little hard to think of really unusual outcomes because they're just, enough constrained by knowledge and experience of seeing a lot of stratospheric sulfates. If we use some other kind of aerosol, I think the uncertainties are bigger. I think there are more uncertainties when those aerosols rain down into the upper troposphere. But I think the biggest uncertainties are kind of the way this interacts with some other pieces of climate feedback that we don't understand well enough.
Where do you see SRM research and politics going in the next decade?
Well, I don't think my record of seeing stuff is very good. So I feel like I often say this to reporters, and I think it just seems glib, but I'm going to say it to you and then we can expand on it. But I really do believe the stuff that came from the super forecasting community that's looked at this, that people who are too close to things do a less good job of predicting the future than people who are further out. So I truly think I'm not good at answering that question. And at some level, I just don't really try to. I kind of concentrate on taking the next step. I do have a bunch of opinions about what I would like to have happen, but you're asking me to handicap what will happen. And I guess I'd say if you draw a trend line through some measure of the acceptability of doing research on this topic and the flow of money and papers, then that would say in 10 years, it really will be some mainstream chunk of climate dialogue where there will be larger research enterprise and it'll be much more integrated into mainstream of climate science and policy. I'd say that that's the extrapolation of the trend line, not that I could quantitatively draw an exact trend line, but I don't have much confidence that'll happen. There may be some kind of peak where people just have enough of this topic.
One last question on SRM. You've been involved in trying to get out some outdoor experiments or outdoor research off the ground. That's been a difficult area. How important are outdoor tests, experiments, and research of SRM to reducing important uncertainties?
They'd be useful. So I'd say that if you really were sort of in a rational environmental cost management, environmental risk management sense, and you actually were a well-intentioned human that was kind of contemplating deploying this in 20 years, I think you would do a whole lot of little experiments because they would chip away at uncertainty. Whether they really change the big picture or not is unclear. I think people often falsely imagine this is sort of the beginning of this science. And so one or two experiments might change a lot. But the right way to think about it is there's like this half century, depending on the exact topic, but long history of science, say on stratospheric aerosols or ozone or atmospheric circulation. And there's some specific questions that are particularly relevant for some kinds of solar geoengineering, like the way that aerosols behave in the stratosphere require experimentation, both field and laboratory experimentation. There's ideas about using solid aerosols, which really might have advantages, and we just don't know how to disperse solid aerosols in the stratosphere. So that really requires some practical experimentation. We know that sulfate aerosols have organics in them in the real stratosphere, and that would change the way they stick together, and we don't know that. So I think one aspect is there's a whole lot we don't know, be especially relevant if we choose to do something other than just the most obvious adding sulfuric acid to the stratosphere. I also think that practically experiments are just kind of a natural part of the way you develop the observational infrastructure and the scientific infrastructure to understand what's happening, not to the large scale climate response deployment, because that is sort of unobservable in some direct way, but to the more local response of the aerosol field to some kind of subscale deployment. Heterogeneous versus homogeneous formation of cirrus clouds is really relevant for cirrus thinning. And there are certainly experiments that could help you understand those things, but they're not likely to like dramatically change the landscape. So on the one hand, I think there's a certain over excitement on both sides. I think the experiments are not going to dramatically change things, or they're not likely to, but even incrementally improving our knowledge would be really useful because it's low cost to do it, both in certainly very low risks and low monetary costs. So I think it's worth doing the research, but I don't expect the research to dramatically change things.
Ice sheet engineering, or ice geoengineering, if you will, is a topic that I've heard about here and there over the last few years. And maybe I've never taken it seriously. The idea of moving mass always just strikes me as a bit fanciful, but maybe I'm wrong. Why should there be more interest, or should there be more interest in ice sheet engineering? And if so, why?
Yeah, so it's very exciting to kind of come to things as an outsider. Like, I'm not an expert. I may never publish a paper in this myself, but I've been running this program. We just ran a kind of amazing meeting here run by Doug McHale and Meghana Ramanathan and John Moore that brought together one of the probably most diverse group of senior scientists ever to work on this. And then there's another even twice as big meeting in San Francisco just before AGU that is, things are moving really fast in this topic. So I've been listening a lot. I'd say maybe the answer to your question is that there are at least some methods, really most of all these seabed anchored curtains, that might be feasible. And feasible in the sense that you're not moving a lot of mass. So the idea of the seabed anchored curtains is that for the marine glaciers that are melted primarily by this warm water from below, water that's flowing in narrow channels at depths of a few hundred meters to warm the base of the glacier, and then fresh meltwater is flowing out on top. In a situation like that, as you have it at Thwaites, Pine Island, if you just slowed that inflow of warm water, you might have a significant effect in reducing this marine ice shelf instability. The idea that once the ice melts back in a place where the retrograde, where the seabed is descending, that's the instability. If you slowed that melt, you really might slow the instability quite a lot. And these seabed anchored curtains seem like a structure that's pretty lightweight. You're just trying to add drag to the flow of water, and you're doing it just in the lower part of the basin. They don't have to stick up at the surface. And these don't seem radically different from engineered structures that people have built for anti-submarine curtains or for fish farming or a variety of things. So you talk to actual marine engineers and they don't laugh at the idea. So I think there's something there that is plausible. And there's a bunch of talk about cooling the bed or pumping water that feels to me less plausible, but worth at least some engineering effort to understand what's doable. I don't want to overstate it, though. I think there's just a huge amount we don't know about actual cost to build these curtains, environmental consequences, a bunch of design questions, and really about how much difference it would make to the probability of, say, the Thwaites Basin collapsing to have the curtains. I think we really don't have a good study of that. So there's a lot of uncertainty. But I think it's clear that the politics of this are very different from solar geoengineering. It's not in some sense clear why they are. So in this whole meeting, where we had some people who I really expect to be very skeptical, the meeting we had here, and there will be a meeting report, nobody was really pushing back and saying that we should do research. Nobody was saying we shouldn't do this because it will give a license to fossil fuel emitters to emit. And it's not really obvious to me rationally why that's true here and not true for solar geo. I don't think there's a clear rational difference. It's somehow just feels less like a moral hazard, but I don't think that shows you how much of this is just based on people's feelings, not on something rational.
Stepping back a bit towards climate change more generally, you've been involved in climate change science and policy now for well more than 30 years. What do you see as your greatest contribution?
I don't know. I mean, I think it's for other people to say. Well, the obvious answer is I've helped to make this topic of solar geoengineering more visible and to advance a certain way to think about it that, from my perspective, is reasonably transparent and cares about environmental impacts and policies. But obviously, other people would have really different opinions about that. And I myself worry that, of course, there's ways it may backfire. It is possible that this will be used as some giant excuse to avoid emissions cuts. But I think that's certainly the biggest thing I would say. I think I helped a little bit in this stuff that we did with Jim Anderson and I did of trying to get people to think about the need to make really accurate observations of temperatures from space. People were focusing too much to signal to noise, and they weren't thinking enough about the fact that you want to leave a long-term record that's really high accuracy. And I think that satellite mission failed. I think it had some impact on how people doing that think about it. I think the stuff on wind power and climate, there's now 400 papers or something, and it's clear there really are local impacts, and it's clear that there's some limits that matter. And I think I wasn't the very first person to do that, but it was the first high profile paper to do it. And I think it had some impact. In atmospheric science, I guess there's other stuff outside, but that's atmospheric science.
Flipping the question around a little bit, not 180 degrees, what were you wrong about?
Oh, well, so I think a bunch of things about technology. I mean, I think the biggest one, the obvious one, and the one that's sort of most rewarding and clean to be wrong about is solar. I just did not think that solar PV would get cheap this fast. And I think a lot of the reason that I and others were thinking a lot about the need to develop, say, CCS on electric power was because we just didn't think solar would get this cheap this fast. And in hindsight, it's completely fantastic. And I even worked with my colleague and student one to develop a careful little quantitative argument showing the solar learning curve was flattening out. And in hindsight, we were just completely dead wrong. So that is kind of really refreshing in a way. That's the most obvious thing. There's plenty of others, but maybe leave it there as a really big one.
You and Pete and I operate in the context of a climate change community, if you will. Scientists, policymakers, experts of politics, journalists, etc. What's working in this community? What's functional here? In what ways is this community currently helpfully advancing climate change issues in a way that will ultimately achieve widely held goals?
Well, I mean, I want to start from the most observable thing, all this hardware actually going into the ground. So the flows of wind and solar and batteries are just stunning. And the beginning of some of these other, I mean, so I asked her sort of atmospheric science stuff I've done, but I think stuff I did was be early in trying to articulate the potential importance of biomass with capture. I think kind of one of the first two papers, and I helped the IPCC and the one in that first CCS thing to really had to push against a lot of resistance to get that kind of in there. And I think there's some limited ways that there are actually, of course, commercial operations now and more starting. And I think there may be ways in which it's a little marginal way that we can do some permanent carbon removal. And then for DAC, I was more started as a critic, pushing back against what Klaus Lackner had done. But obviously, in hindsight, I'm one of the people who helped to kind of drive the actual commercial development of DAC. So one of those things may turn out to be useful. It's hard to tell. I regard them as sort of buying an option that can be used depending on the kind of public policy choices.
Now I am going to flip around the question 180 degrees. When you look at the climate change community, what's it doing wrong? What's dysfunctional?
The first answer is like so many things, but it's also true that when you're close to something, you just only see the dysfunctionality. But you step back from it, and the climate community actually has succeeded in getting this on the international agenda and getting stuff done. I think on the deployment of emissions reductions, which is the fundamental thing that needs to happen, I think that there's an unwillingness to realize that as we've moved from the very early kind of playing phase to the beginning of really doing it at kind of 1% of GDP, that we really do have to be more serious about costs. that you can't just have every advocacy in government pushing whatever's their pet thing, because at some level, costs really matter. And there really will be public pushback against hard costs. Indeed, The Economist has a good summary article of the way the kind of climate backlash has begun. And I think that there needs to be a lot more kind of hard-nosed rationality about where public, either direct money or indirect money through regulatory controls, is getting spent, because there really are enormous differences in kind of dollars a ton avoided between some things that we're doing that are really sensible and pretty cheap, like some of the really large industrial solar and wind build-outs in grids that are relatively high fossil, which are just like hugely cost effective, and other stuff which is hugely ineffective or, very, very expensive. So I think more rationality about that is crucial. And some of that demands a level of kind of realism that the climate community isn't very good at. I think the other thing that I really see as problematic is the role of too many little startups and kind of driving the conversation through the press in a way that's kind of weird, in a sense that it's not really that much money moving in them, and it's not actually that hard to create a startup in this world. And yet somehow those startups are reported as kind of the cutting edge of what's happening. And yet often they're actually not very important as a part of what's happening, because a lot of the way these big technologies actually move is in large industrial enterprises, not in startups.
What about climate change, or more generally, what about the world keeps you optimistic? What's your source of optimism?
Well, it's a little hard to be so optimistic in a day of two active wars or conflicts that are as hideous as the ones we have now. I really do worry about political instability and violence. I always did. I was very politically kind of engaged as a young person about nuclear proliferation and risk. And I see this as a really pretty dangerous place, more than it was a decade ago. I think that, yeah, I guess I'm giving you negative answers. I mean, the positive answer, you asked for optimism. Positive answer, I mean, it's funny. I mean, I think a lot of the climate activist community would see what we're doing on climate as this huge failure because we're not going to meet some 1.5 target. I actually see the collective action to begin to transform the energy system, and maybe the fact that we're about peaking fossil fuels, is kind of a giant win. And I wish it was a bigger win, but it seems to me a pretty darn big win in broad environmental battle. So I'm optimistic about that.
With that, let's wrap up. David Keith, thank you for joining us on Challenging Climate.
Thanks a lot for being here.
Well, thanks for listening. Please rate or review us on Apple Podcasts and elsewhere, and consider supporting us on Patreon. That's patreon.com/challengingclimate.